Uh, the first one, I think I finished a couple of years ago, and the second one I finished about 4 years ago. So everything's a little bit hazy. So this is just to make excuses before the talk, but let's see what happens. Okay, so the first talk is about what's called the localization game. So to start off, I've got to have to share the screen, right? Okay, so everybody can see the slide, yeah? Can anybody see the slide?
We can see the slides.
Ah, good, okay. Okay, so I'm going to talk about the localization game. Okay, so you have a graph, G, and let's say for a vertex V and a set of vertices, capital W, we'll say that sigma is short for signature. The signature of V and W are this collection of distances between the vertex V and each W in capital W. And so the game is to try and use this signature to identify where V is. So you're given a big set W, you're given the signature. Can you use that to determine where V is actually where V is? Okay, so this was, I think the first, I don't know. So maybe this is probably a game version of the dimension. So the dimension of a graph would, in this, or actually called, I think they call it the metric dimension, is the smallest size of a set such that you can use that set to identify a particular vertex. In other words, it's the smallest set size so that you can find a set W such that every vertex has a different signature. Okay, and now what is happening? Oh, it should be here. Okay, so this was studied by Bolabash, Mitski, and Pavel Pralat. Sorry, it's not Pravat. I'm sorry, Pavel, I couldn't do the L properly. Couldn't get the dash through. So anyway, we're going to assume that we're in a dense case for most of the talk. Although the paper by on the dimension covers lower p as well, and we have this parameter rho, p squared plus 1 minus p squared. We see that is if you're given 3 vertices u, v, and w, it's the probability that u, w, and vw has the same signature or something. You know, either they're both neighbors of, either u and v are both neighbors of w, or u and v are both non-neighbors of w. So that's obviously important from the point of view of the signature. Okay, so you see from this that you've got some good bounds on the dimension. All right, in this particular case, it's fairly simple. And so in particular, if p is a constant or p is little o n to the 1, it's asymptotically correct. So this is the dimension. So the question is now, what is the localization game? So the location game, okay, it's usually termed in cops and robbers, but I thought at the moment we don't want to talk about cops and robbers. So let's suppose we have a fugitive x, and the fugitive starts at some vertex v0 and is allowed to move along edges v0, v1, v2. And there's a pursuer, y, who's trying to figure out where x is. And how does y do this? Well, y is instead of, it's not, so in the dimension game, say, you'd only be allowed to choose one set. But here, y can choose a whole sequence of sets, and they'll all be the same size. And somehow, magically, when y chooses the set Wi, it learns the signature of Vi and Wi. And then it sort of adapts to that and tries to figure out where the fugitive X is at the current moment. Okay, so what are the results on this? So they'll, oh well, we know. So Y will win if they can identify where X is in after a finite number of steps. And otherwise, capital X wins. And we'll say that a zeta of G is the smallest K such that Y can win. Okay? So what do we know? Okay, so for the diameter 2 game, with G as GNP, with Dudek and Pegden, we sort of sorted it out to a certain extent. So we said that zeta of GNP is, well, it's given by the expression at the bottom. And what you notice is, I suppose that if P is, say P is a constant, we don't make any progress because, well, you can't. But if P is like n to the 1 over n to the epsilon, then eta will be a constant, and you can make some progress here. And by progress, I mean that zeta will be less than the dimension. We don't have it's not type, and the constant C, I can't remember what it is, but it's just some absolute constant. And by and large, I'm not actually going to, so this is a short talk. I'm not going to say very much, and even though I don't say much, I won't even say much about this particular case. And we'll stick to, by and large, we'll stick to this case. Okay. Okay, so because the diameter is 2, the signature is just the 0, 1 vector, 0, 1 to the capital W. And this is where the rho comes in. The probability that V and V dash have the same signature is a rho to the size of W. So that's where the rho comes in. So obviously, the bigger rho, the less likely the two vertices are going to have the same signature. Okay, so you've got more, with a big W, you can actually figure out where the fugitive is. Okay. Okay, so lower bound, this was proved by the following. If you take, okay, let's look at the form. So X, so for a fixed set S, so for a set S of size K, so capital X U S is the number of pairs, right, which are contained in the neighborhood of a set U. So we've got a U, the number of pairs in the neighborhood with the same signature as U. That can't be the same. I think the sigma phi is sigma W. That's probably I can't say it's a typo, it's handwritten. Okay. So the point is that using, I think we, in that paper we used, well, I can remember we used Stephen Swen's lemma. Okay, to prove that with high probability, if K is small, then X of US is non-zero for all U and all S. Okay, so there's always a pair in the neighborhood with the same signature. That means that the fugitive can avoid being captured because there's always a choice of 2. Okay, and this is just a straight calculation based on Swen's inequality. Okay, upper bound. So this upper bound works. Well, it works in what we could call in a pseudo-random setting. So we just have to assume that the degree of vertex is approximately NP, and the co-degree is approximately np squared. And the D of VW is the set of places where V and W have different neighborhoods. So right, so I pick something. If I pick something in D of VW, I can distinguish between V and W. And so, okay, so how do we start? So the pursuer has to start by choosing a set. And okay, so what the pursuer does is choose a random K set. Now I should say that in the published version, S1 is an arbitrary set. So in the actual published version, there's an error. And we didn't fix the error until we started thinking about the sparser case, where it's multiplicated. And for a while we were stuck. We thought we were going to have to withdraw the paper, and then we figured out that randomness comes to the rescue. So we'll say S1 is a random K set, and we keep track Z1, which is the number of pairs VW with the same signature in S1. And what we're going to do is try and choose a set S1, S2, S3, S4 until this signature goes to 0, and then we're done. Okay, so all you have to do is figure out, you have to do a bit of calculation. You work out the expected size of Z1. And that's not a terrible calculation. And it comes out to be n to the 2c eta. And eta was something which I saw back before, like log 1 over p over log n. So what does this mean? It means that with high probability, after one round, we've reduced the, let's say we've reduced the, not the ambiguity, well, maybe the ambiguity of instead of thinking that the fugitive could be any one of n places, it's now only in at most n to the c eta places. So that is why I put the n in red. Okay, so what we know is, in the next round, the fugitive will either be in R, right, which is some large set of size omega and theta, or the union of n to R. So what that means is we can replace the red n by the red 2 omega n to c n to p squared times rho to the k. So the expectation of Z2 is much smaller if you choose, if p is small, right? And c eta is small. Right? And then, okay, after L rounds, you've got ZL is less than or equal to some formula, and by suitable choices of omega, c, and eta, etc., this goes to 0. And so after L rounds, the fugitive has been caught. Okay, so that basically is everything I'm going to say about the 2 case. The more general case, it has the same sort of philosophy, right? Okay, but now the question, the philosophy is, so now instead of being either at distance 0 or 1 from a vertex, you can be a distance between 0 and 1 up to the diameter. And for k too small, x can basically stay at the maximum distance from all the vertices in S. And there's lots of choices. So so the signature always looks like D, 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 where D is diameter. And there's plenty of choices. I must say, so the philosophy is the same, but the work is much harder. And for large K, we have the same philosophy. We have the dVW, but now this is the union over NJV and NJW, where NJ is the number of vertices. This NJ would be the vertices at distance j from V. Same philosophy, much more work. And this shrinks more quickly. Okay, so that's basically the talk. So let me just give some questions that I thought of, just to round it off. Okay, obviously, now Pavel may know, worked on this, but I haven't. So for other graphs, I don't know whether we know GNP, it's certainly not in the paper we published. What's GNP at the threshold for connectivity? So for a sparse graph, if the robber was foolish enough to put himself in or herself in a little tree, and then it serves them right for getting caught. Otherwise, they would go into the giant component, and then the question is, what's zeta for the giant component? Another one might be the preferential attachment graph. Or then if you want other non-random graphs, you think about the cube. So I don't know what's been done on this. There's another question, which would be, we were saved by randomness, okay? We started off with just arbitrary, we thought that arbitrary sets would do, but that wasn't true. And we never really figured out a good deterministic choice for the SIs. Now, I suppose since there's a random choice, there must be a deterministic choice. This is a game, but is there something which you could actually write down? Yeah, so, right, well, okay, so that's it. So, and I'll move on to the second talk, which is very sparse. So this was a paper with Wesley Pegden, and it's called Looking for Vertex 1. Okay, and GN is the preferential attachment graph with n vertices. So what do we mean by the preferential attachment graph? Well, it's a sequence of graphs G1, G2, G3 up to Gn. And how do you get from Gi plus 1 to, how do you get to Gi plus 1 from Gi? Well, you add m random edges. And when you add an edge, ur plus 1, you have to choose your neighbors in Gi proportional to their degree. So this is a sort of, I suppose, the first real-world model of a real-world network. And it's the simplest one. It's quite nice. Okay, so let me explain this problem. So the problem is you've got to start at an arbitrary vertex, and you'll find your way to vertex U1, because they're called U's, right? U1, using a local algorithm. Maybe I should go forward. It's easy to find V1 if you see the times at which the vertices are added. Because all you do is you move to the oldest neighbor, and then the oldest, and the oldest, and the oldest. And I think after about log n divided by log n moves, it will be there. And we assume that when you get to vertex 1, there's a flag at vertex 1. I like to think it's like Scott of the Antarctic and arrives at the South Pole and sees the flag there left by Edwardson. So anyway, so there's a flag at vertex 1, and when you get there, you know you're there. Otherwise, you don't see every other vertex has no flags, and you don't know their ages. Okay, but the thing about the preferential attachment graph is that the older you are, the higher your degree. I suppose it's sort of true in life in some sense. So, but not knowing we want to know the times, so we use degrees as a surrogate, because older vertices tend to have higher degrees. Now, one is tempted, okay, so there's this. So there was an algorithm by Borg, these guys, and they used an algorithm that ran in log to the 4n steps. And what that algorithm had to do, you had to remember your complete history. Our algorithm is simpler, and and has less storage, and it's faster. But I think, to be fair to these guys, they just wanted to prove something that's polylogarithmic, and once you've done that, you don't necessarily have any energy to do any more. And this one was quite difficult. And when I read it, I think, my God, you know, how do we do that? Okay, so what's our algorithm for, yeah, so looking at this, one is tempted to just say, okay, well, why don't you move to your highest degree neighbor? Well, I think in that sense, there's a proper possibility you'll get stuck. You keep going backwards and forwards. So we do something similar to that. So what we do is the following. This is the algorithm, which is like DCA, which I can't remember what it is for. Descending. I can't remember what it stands for now. Anyway, so first of all, you do a random walk. You start anywhere. You know where you start. Presumably, you don't start at vertex 1. You do a random walk until it's mixed. So that only takes all the log n steps with high probability. By mixed means we're very close to uniform. So we start at V1, and we'll keep track of the steps, call it T. So let's suppose you're at VT at time T. So you look at all the neighbors. You've got at least m neighbors. So CT will be the half m neighbors of largest degree. So the sort of naive algorithm says move to W1. This sort of algorithm says choose randomly from the first half m largest neighbors, and that seems to work. So you do that, and you do that until the degree is big, and then you have to prove that the degree gets big, and that takes a lot of work. They say that once you get to the degree at least square root n over some strange power of log, you just do a random walk on the vertices of high degree until you reach vertex 1. Now, I don't want to, of course, I'm getting close to the end of the talk, so I'll just skip most of the stuff. And let me just say a couple of things. The first thing we did is we proved that this is what we proved. Basically, that in the main loop, the expected age goes down by 3/4 every time we do it, up to some big time. And unfortunately, this is not expected value given the history. This is a sort of unconditional expectation. And that makes a problem for us, because if it was conditional on the history, it would be trivial. And then we'd get a log n. Instead, we have to do something more complicated. Nothing terribly complicated, but we gain an omega. Okay, if anybody wants to try and get rid of the omega, they're welcome. It's very long, and when I tried to read it today, and I just can't remember. One of the problems is you can go to a younger vertex, and there's lots of calculation. Anyway, so there we have it. That's my excuse. So eventually, you must reach a large degree vertex. Now we look at the graph that's induced by the vertices of high degree. There are not many of them. There's only all the log to the 9th n of them. So the cover time of this graph is little of log n. So, you know, what's the cover time? When you wander around this graph, and you'll have visited, in the cover time, you'll have visited every vertex. This is an expectation. And so, of course, if you visit every vertex, you're going to visit vertex 1, because its degree is bigger than that. And you'll have found vertex 1. And that's the end of the story. Okay? Anthony, you still there?
I'm here. Yeah, thank you very much, Alan.
That's it. Yeah, I'm done. I am done. Sorry, I should have said thank you, but thank you anyway. Thank you all for coming.
Thank you
Anybody
very much,
still
Alan,
left?
for the talk. It's very good.